Today we'll cover section 3.2 in our continuing study of logic. 3.2 is called Truth Tables, Equivalent Statements, and Tautologies. In the previous section, we learned that truth tables are used to list every possible way that a simple or compound statement can be true or false. And we covered two of what will eventually be 5 basic truth tables whose values will allow us to tackle many more complex logical statements than we've done so far. So these are the two we've already covered. The conjunction, which is the and we learned that an and is only true when they're both true. And the disjunction, or the or, and we learned that a disjunction is only false when they're both false. True when they're both true, that's and. False when they're both false, that's or. Those little memory aids help you remember what the table values are without having to strictly memorize the tables themselves. We're going to add a third one now called the negation. The negation of a statement P is tilde P, or it's just a squiggle, tilde P, and of course it has a truth table as well, and it simply changes the truth value to its opposite. The negation changes the sign. The negation changes the value of its truth value to the opposite. So the negation is false whenever the original statement is true, and is true whenever the original statement is false. So our little memory aid is for a negation, true becomes false and false becomes true. For example, if the statement said the ball is red, the negation would be the ball is not red. If the original statement is true, that is, the ball really is red, then the negation is false, which says the ball is not red. On the other hand, if the original statement is false, then the negation is true. It simply changes the truth value to its opposite. Notice that manipulating logical statements is a lot like using the English language. For example, if I ask you, "What is your name?" you must analyze the sentence in order to properly respond with your name. Perhaps my name is Laura, my name is Tom, whatever your name is. Similarly, if I give you the logical statement T and F, you must analyze it in order to give the proper response, which of course is false. So there's a really close analogy with the English language here if you think about it. When you're doing this sort of thing, you might say that you're operating in interpretation mode. You're interpreting what the symbols mean. When operating in interpretation mode, we use basic rules to tell us how to respond to the logical statement, for example, T and F. The basic rule we need here to interpret it is that it's only true if they're both true. Well, they're not both true here, so that tells you that the result is false or the answer is false. So when we operate in interpretation mode, we're just using a basic set of rules to simplify a logical statement. For example, I might ask you to construct a truth table for the statement P and not Q. What you typically do is make a P column, a Q column, where you have all possibilities. Both P and Q could be true. Each one of them in turn could be false, or they could both be false. And then to make it easier, most people do this by adding columns that correspond to the pieces of the complete compound statement. So I see a not Q to the right of the and, so I'm going to create a not Q column. And eventually I want to do P and not Q as a whole statement, so I'll make a column for that. So you can sort of see you start off with the P and Q columns, then you look and see the pieces. There's a P piece, but you've already taken care of that. There's a not Q piece, so you put that in there, and then the whole statement gets its own column. It just makes it easier if you do it that way. Because you'll see as we go through this, if I want to do this, the first thing I want to do is fill in the values for not Q, and in order to fill in the values for not Q, I have to look at the Q column. And remember, the not is the negation, which changes the truth values. So true becomes false, false becomes true, true becomes false, and false becomes true. And notice I'm looking at the Q column to figure out what not Q is. Now that I've done that, I move to the last column, and the last column has a statement P in it. So what I can do is just lift the values of P on the far left and just transfer them over under the P in the last column. And then I can do the same thing with the not Q. I see on the other side of the and there's a not Q, so I can simply lift those values and slide them over under the not Q. And notice that between those two things is an and symbol, so I'll just push the and all the way down. And now I need to evaluate the and in that last column. Remember that a conjunction, which is an and, is only true if both statements are true. So if I look at the first one, they're not both true, so that means the statement is false. Looking at the next one, they are both true, so the statement is true. In the third case, they're not both true, so the statement is false. And in the fourth case, they're not both true, so the statement is false. So you go down there and you interpret and by remembering that it's only true if they're both true. And that gives you the complete solution for that truth table for that original statement. Pretty simple if you take it one step at a time and create those intermediate columns when you need them. Sometimes we're asked for the truth value of a statement that doesn't require us to build the entire truth table. For example, this problem simply says determine the truth value of the compound statement given that P is a true statement and Q is a false statement and R is a true statement. And the logical statement is P or, and then you've got in parentheses, not Q or R. You don't have to do the whole truth table if they tell you that P is true, Q is false, and R is true. All you need to do is note that P is true, Q is false, R is true, and then plug in a T for the P, plug in an F for the Q, and plug in a T for the R. And if you do that, you get the statement true or, and in parentheses, not false or true. And once you do that, you can work your way through. And notice you want to get rid of that negation first. That's probably what you want to do. Notice that not false is true. So that statement turns into true or, and in the parentheses, true or true. From there on out, you want to work inside your parentheses first. True or true is true. And then you're left with true or true, and true or true is true. Remember, with or, it's only false if they're both false. So you end up with a statement value of true. And notice you didn't have to produce the entire truth table if you already know the values of each individual statement. By the way, there's a name for a statement that's always true. It's called a tautology. And here's an example to work through. You're going to see that this statement is actually a tautology. It's always true. Let's just do it with a truth table. Add the extra columns. Remember, you're going to start out with a P column and a Q column with every possible combination of true and false. You notice up there there's a not P inside of the whole statement, so you make a not P column. And then on the left there's a P or Q, so you'll make a P or Q column. And then you'll want a column at the end that encapsulates the entire statement. And from there you just move from left to right. So I'll start off, I form the not P column by taking the opposite truth value of the P column. So if P is true, not P is false, and so on down the line. That gives me not P. Then I move to the next column and notice that there's a P on one side of the OR and a Q on the other side of the OR. So I'll just take those P values and move them underneath the P values in that middle column, and then I'll take the Q values and move them underneath in the Qs. In the first row, that leaves me true or true, true or false, false or true, and false or false. Now remember, with an or, it's only false if they're both false. So I might notice there's only one place where they're both false. You might just notice that that's first and the rest of them have to be true. If you can identify the false one, the rest of them have to be true, or the false ones had there been more than one. And so there you go with the P or Q column. Now you want to keep moving to the right, and you notice that for this last column you have the P or Q done, so just transfer those values over. True, 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 false underneath the P or Q, and you already have not P done in an earlier column, so transfer the not P values over underneath the not P. And remember, it's an or in the middle. So we're doing or again, and an or is only false if they're both false. If you look through there, there is absolutely no place where they're both false. So that means they're all true. Hence the name tautology. And a tautology is a logical statement that's always true. By the way, if they all turn out to be false, it's called a self-contradiction. If they're all true, it's a tautology. If that last column turns out to be all false, it's called a self-contradiction. Another thing about these truth tables, you can tell how many rows are going to be by looking at how many distinct simple logical statements there are. In fact, if there are n simple statements, there will be 2 to the power of n rows. For example, if you take this one, there's a P, there's a Q, there's an R. So there are 3 simple statements. So 2 to the third is 8, and that tells you you'll have 8 rows in the truth table. So if you had a case where you had a P, Q, R, and S, which would be 4, it'd be 2 to the 4th, which would be 16, and so on and so forth. So you can always tell how many rows your truth table will have by counting how many of these simple statements there are in the compound statement. Let's go ahead and complete the truth table for it. Again, my suggestion is to put in the columns for the intermediate steps. If you look back, you notice there's a not R in that bigger compound statement, so I'll actually make a not R column. You'll also notice there's a Q and not R. I'll make a Q and not R column. And of course, the last column is going to have the statement you're trying to get the truth values for. Now that I got there, I notice there's a not R column that I need to fill out. So if you sort of start on the left, I'll take the R column and change all the truth values to their opposites. True becomes false, false becomes true, all the way down. Then I move to the Q and not R column, which is the next column. Notice I already have a Q column, so I'll move the Q's underneath the Q's. And I already have a not R column, so I'll move the not R's under the not R's. And then I'll notice it's an and between them. Remember, for an and, it's only true if they're both true. So if you just go down and look, that first one's not both true, so that'll be false. There's a both true there, so that'll be true. That's not both true, so it'll be false. That's not both true, so it'll be false. That's not both true, so it'll be false. That is both true, so it'll be true. That is not both true, so it'll be false. That is not both true, so it'll be false. Finally, I move to the last column, and notice I have a P there, so I'll go back to the original P column on the far left and move it over under the P. Then I notice I have a Q and not R column, and I can move it underneath the corresponding statement. And then I notice there is an OR symbol between them. And remember, for an OR, it's only false if they're both false. So I scan through them. That's not both false, so it's true. True is not both false, so that's true. That's not both false, so it's true. That's not both false, so it's true. That is both false, so it's false. That's the only case when an OR is false, when they're both false. The next one is not both false, so it's true. The next one is both false, so it's false. And the last one is both false, so it's false. And there you go. You've done the truth table for that problem. On the actual WebAssign homework, sometimes these truth tables look slightly differently because they're going to ask you to do drop-down boxes to pick your trues and false. I want to show you what it might actually look like in WebAssign. You might get something that looks like that. So you've got to practice what this means. And part of it is probably pretty common sense. For example, that Q column is exactly what we were doing before. You simply take the Q values in column 2 and move them underneath the Q values in that last part. Same thing with not P. You've got to take the negation of P. So if you go to the P's and take their opposites, the true becomes false in the first row, the true becomes false in the second row, the false becomes true in the third row, and the false becomes true in the fourth row. So you're actually doing the negation in your head, and you're moving the opposite values over. Then you notice that they're asking you to AND those things. In other words, there's an AND between each of those true, false, false, trues, and all those combinations. So you want to do an and an AND is only true if they're both true. So you look there, that true, false is not both true, so it'll be false. The second one, false, false, not both true, so it's false. The third one is both true, so it's true. And the last one is not both true, so it is false. Now, notice here, once you've combined the Q's and the not P's to get the ands, those things that are highlighted right now, those two columns that are highlighted, they're essentially used up. You're only paying attention now to that false, false, true, false column because they've been combined together into that middle column. So what I think of is you're only looking at that false, false, true, false column until you get to the very end, because you're going to OR that with the not Q column on the very end. You could actually take a pencil or something and just mark them out because they're not relevant anymore. Only those shaded columns matter now, and I'm going to OR them. So I have to get that not Q figured out. Well, if Q is true, then not Q is going to be false. If Q is false, not Q is going to be true. If Q is true, not Q will be false. And if Q is false, not Q will be true. So now I'm ready to actually complete the OR with those two shaded columns. And remember, an OR is only false if they're both false. The very first row is both false, so that'll be false. The second row is not both false, that'll be true. The third row is not both false, so it'll be true. And the last row is not both false, so it'll be true. So that is your truth table for the original statement. Practice this, and if it becomes necessary, you can actually copy this down onto your paper so you can mark things out if you think that's helpful. To continue the language analogy, in addition to that interpretation mode where we use our basic rules to simplify logical statements, and something called the translation mode, which is nothing more than translating from logical statements to English sentences or vice versa, we also have special cases or rules, just like you have in English, that apply only in certain circumstances. For example, the I before E spelling rule in English. This sort of corresponds to it. There are similarly special cases or rules when you're working with logical statements, and one pair of special rules is called De Morgan's laws. And there are two of them. De Morgan's laws for statements says for any statement P and Q, the negation of P or Q is not P and not Q, and the negation of P and Q is not P or not Q. Now, it might look a little strange at first, but it's very easy to interpret this. In the first statement, it says that if you negate an OR statement, you get an AND statement. So the OR on the left side becomes an AND on the right side, and the tilde, the negation symbol, distributes through just like a minus sign would if you were doing regular algebra. So the negation of P or Q is the negation of P and the negation of Q. An OR becomes an AND, and the negation passes through like a minus sign. And on the next one, it says that if you start out with an AND, the negation of an AND becomes an OR. And again, the same idea. You start off with an AND on the left. If you negate it, you'll end up with an OR on the right, and the tilde, the negation symbol, just distributes through as if it were a minus sign. So the negation of P and Q is the negation of P or the negation of Q. OR becomes AND becomes OR, and the tildes distribute like a minus sign. So these are really easy to remember. De Morgan's laws can be used to restate certain English sentences in an equivalent form. For example, I might ask you to use one of De Morgan's laws to restate the following sentence in an equivalent form. It is not true that I graduated or I got a job. You need to think of this in terms of the symbols. The it is not true that is like the tilde. It's the negation. Notice that we're using the comma for grouping just like we have in earlier cases. So when that comma there means that everything to the right of comma is grouped together. So that I graduated or I got a job is essentially in parentheses. It's grouped together. So I graduated or got a job, that together is grouped because of that comma. And we've done that earlier, so it's the same idea. The comma is telling us to group everything on the other side together. If you think of I graduated or got a job, finding the negation of that, it's like the first formula. It's like the negation of P or Q. So that would be equivalent to the negation of P and the negation of Q. So the negation of I graduated would be I did not graduate. The negation of I got a job would be I did not get a job. And remember, the original OR, when it gets negated, becomes an AND. So the statement, it is not true that I graduated or got a job, is equivalent to the first one of De Morgan's laws, which allows us to reinterpret the sentence in an equivalent form as I did not graduate and I did not get a job. So that's an example of using one of De Morgan's laws to change an English statement from one form to the other. And in particular, that English statement was the negation of an or. And I won't do it here, but I will say that I could do another example where I was doing the negation of an and. It would work the exact same way, except the and on the left would become an or on the right, and I would still do the negations of the P and Q exactly the same. We're continuing our study of logic in section 3.3 on the conditional and biconditional. Back in section 3.1, we learned that truth tables are used to list every possible way that a simple or compound statement can be true or false. The next of the 5 basic truth tables that we're developing, this will be number 4, is called the conditional, sometimes called the if-then. The truth table for the if-then has only one case where the result is false, and that is if the P is true and the Q is false. This is probably the hardest one to remember, but it's the only false case for the conditional. T is true, F is false. T implies false is false. All of the other cases are true. So even though it's probably the hardest to remember, you have to focus on the one false case and just remember that the others are true. You might say this in words: a conditional is false only when the antecedent, sometimes that P is called the antecedent, is true and the consequent is false. Antecedent is the P and consequent is the Q. For example, if I gave you the statement, if you need help, then I will help you. This compound statement is false only if the antecedent is true and the consequent is false. If you need help, then I will help you. You need help is false. I will help you is true, produces a false compound statement here. It's the only case where it's false. Now we're up to 4 of the 5 basic truth tables we will need to complete our study of logic. We started out with the conjunction and disjunction in section 2. We added the negation. Now we're adding the conditional. The 5th one is called the biconditional. Notice that the conditional is an arrow pointing to the right. The biconditional symbol is an arrow pointing in both directions, or a double-headed arrow. The biconditional is only true when P and Q have the same truth values. In other words, they're both true or they're both false. So if you look at the truth table for the biconditional, it's only true if you get P true, Q true, or if you get P false, Q false. Otherwise, it's false. That gives us all 5 of our basic truth tables. This is sort of a visual summary with the memory aids below them. We've got the 5 truth tables. Rather than memorizing them line by line, my suggestion is to learn the memory aids or create your own memory aids so that you can remember what these tables result in without having to memorize them line by line. For the negation, I would say the memory aid is T changes to F, F changes to T, or you might say the negation changes the truth values to their opposites. However you want to phrase that memory aid so that you can remember it. For the and, the memory aid is it's only true if they're both true. For the or, the memory aid is it's only false if they're both false. For the implication or the if-then, it's only false if P is true and F is false. To me, that's the hardest one to remember. And finally, the biconditional, it's only true if P and Q match. However you want to rephrase those memory aids, there are 5 of them, and you need to be able to say them to yourself so that you can produce those tables if you need to. I referred to some of our work as working in the interpretation mode. These are your tools for working in the interpretation mode. Now let's see if we can take some more complex logical statements and apply what we've learned here to those statements. Sometimes we actually need to leave interpretation mode and move to translation mode. And this is when we need to translate from logical statements to English statements or vice versa. So let's practice that a little bit. Recall that statements of the form P implies Q are called conditional statements. Again, the implication, the arrow pointing to the right, has various names. Sometimes you call them if-then. You can call it an implication. You can call them conditionals. Conditional statements can be written in the form if P then Q. Sometimes the word then is left out. If P, comma, Q. It just means that in English language sometimes you leave out the word then, but it's understood to be there. For instance, all the following are conditional statements. If we order pizza, then we can have it delivered. If you go to the movie, you will not be able to meet us for dinner. If n is a prime number greater than 2, then n is an odd number. You don't actually have to have the word then in there for it to be understood to be there. In any conditional statement represented by if P then Q or by if P Q, the P statement is called the antecedent, as I've mentioned earlier, and the Q statement is called the consequent. Occasionally you'll see the word antecedent called hypothesis and the Q called the conclusion. So, identify the antecedent and consequent in the following statements. If our school was this nice, I would go there more than once a week. The antecedent is the P, our school was this nice. The consequent is the Q, I would go there more than once a week. It's just that simple. If you don't get in that plane, you'll regret it. You don't get in that plane is the antecedent. You'll regret it is the consequent. This is just a summary now of what we've said. Sometimes that right pointing arrow is referred to as the arrow notation, but basically otherwise that is just a statement of what we've already said. The conditional statement, if P then Q, can be written using the arrow notation as P with the right pointing arrow, Q. The arrow notation is read if P then Q or P implies Q. And remember, the truth table for the conditional, it's only false if P is true and Q is false. Make sure you get that one right, because at least for me, that's the hardest one to remember. That's the only case where the implication is false. I like to think, sometimes I want to make sure I'm thinking about it right. I'll make up a simple sentence. For instance, if I said, if you need me, I'll be there. Think of it this way. If I said that to you, the only time my statement would be false is if you needed me. That would be like P being true, but I wasn't there. That's like the Q being false. If I said, if you need me, I'll be there, but you needed me and I wasn't there, that would be a false statement. And it's the only time an implication is actually false. Now let's play around with this implication and the conditional notation and do a truth table that involves that. First of all, I like to add intermediate columns. So I'm going to push that off to the side and build my own table where I have intermediate columns. Now we've talked about this in earlier sections. You notice that if you look at the pieces, there's a not R piece of this compound statement. So I'll make a not R column. There's also a Q and not R piece. So I'll make a column for that. And then of course you want a column for the final statement as a whole. So I will take that original truth table and add these columns to make it a little easier to work through the way I've been doing it. Now that I've done that, let's get started. The first thing you want to concentrate on is the not R column. You have the R columns. All you have to do is change the truth values to their opposites and you'll have the not R column. Then you want to go to the next column, and you notice in the next column you have a Q, but you know the values of Q from the second column, so you move those over under the Q. Same thing for the not R. I just produced the not R column, so if I copy that underneath the new not R, I have that, and then I notice there's an and between those two. Now I have to evaluate this and remember the shortcut for the and, the memory aid for the and, is it's only true if they're both true. So if you scan down there, you just look, and every time you see a true and true, you change it to true, and unless it's a true and true, it stays false. So I'm just scanning down here, and I'm not seeing many true and trues. There's another one, true and true, it's true. But until I see a true and true, it's false. And finally, I'm ready to tackle the last column. The last column begins with a P, so I'll take the P values from the far left column and move them over. And on the other side of the implication symbol, I have that Q and not R, so I'll take that column of values and move those over. And then I note that I have an implication symbol between them. So I have true implies false, true implies true, and all the way down the list. And you have to remember, for an implication, there's only one false case, and that's if the hypothesis, I said it's sometimes called the hypothesis, the antecedent, whatever you want to call it, and the conclusion is false. If the hypothesis or antecedent is true and the conclusion is false, then the statement is false. Otherwise, it's true. So if you scan down the list, you're actually looking for true implies false. Well, the very first one is true implies false, so that's false. But that's the only one you're scanning for that turns false. If it's not true implies false, then it will be true. So it's true here. There's a true implies false, so that's false. There's another true implies false, so that's false. That's not true implies false. That's not true implies false. That's not true implies false. And that's not true implies false. So as you scan down the list, you're looking for true implies false. That particular thing is false. The rest of them are true. And voila, you have the truth table completed. There are two more special cases that we need to know. Remember, in the last section, we talked about two cases being the two De Morgan's laws. Here are two more special cases that involve the implication. This has to do with taking conditional statements and putting them in an equivalent form. By examining the two truth tables below, we see that not P or Q and P implies Q are the same values. I'm not going through this again, but if we went through the process of doing the truth table for not P or Q, which is the one on the left, and then we did the truth table for P implies Q, which we just did actually, on the right, you notice they have exactly the same truth values. The shaded column on the left truth table is true, false, true, true, and the shaded column on the second truth table is true, false, true, true. So they have exactly the same truth values. That means that those two forms are equivalent to each other because they produce exactly the same truth values. So what I've shown is that the conditional P implies Q is equivalent to the disjunction not P or Q. And we tend to use this symbol in the middle, not an equal sign, but three horizontal bars as being the word equivalent. For our purposes, we're not making much of a distinction, equivalent, equal, but technically that three-bar symbol is equivalent. So P implies Q is equivalent to not P or Q, and I know that because I looked at the truth tables back over on the left and saw that they produce the same truth values. So that's the first of the new special case rules that we need. Let's practice this. If I ask you to write in its equivalent disjunctive form this sentence, if I could play the guitar, I would join the band. Now what they mean by disjunctive form, if you're looking up at the formula, on the right-hand side there's an or, and an or is a disjunction. So that's what they're referring to. But anyway, back to the problem. If I could play the guitar, I would join the band. The I could play the guitar is like the P. The I would join the band is like the Q. So I'm taking that statement, which is modeled on the left-hand side of that formula, and changing it to the right-hand side. So right now, I've got the left-hand side of the equation done. I want to change it to the right-hand side of the equation. So I form not P. Well, if P is I could play the guitar, then not P is I could not play the guitar. Or Q, which is I would join the band. So the statement I could not play the guitar or I would join the band is logically equivalent to the statement that I started with, which says if I could play the guitar, I would join the band. So that's a simple example of using this equivalent form of a conditional formula. I'm not going to go through this, but we could show that the negation of a conditional can be written as a conjunction. A conditional can be written as a disjunction, an or. The negation of a conditional can be written as a conjunction, which is an and there's the formula. I derived the other one, or at least I showed that it was true. I'm not going to do that here, but it would be just as easy to do as the other. We just take it for granted. An example, write the negation of the following statement. The statement is, if the lines are parallel, then they do not intersect. So the negation of that statement, the lines are parallel is like the P, the if then is the right pointing arrow, they do not intersect is like Q. So forming the left hand side of the statement and changing it into the right hand side of the statement is what they're asking me to do. The P is the lines are parallel. The conjunction is the and not Q would be, if Q is they do not intersect, then not Q would be they do intersect. So the negation of the original statement, if the lines are parallel, then they do not intersect, is the lines are parallel and they do intersect. And that's an example of the second of the special formulas that we are introducing right now. Now recall from our earlier discussion that statements of the form P with the double pointing arrow, the double-headed arrow, are called biconditional statements. And the truth table of the biconditional is given here, and the key to remembering it is it's only true if they match. If they're both true, the biconditional is true. If they're both false, the biconditional is true. Otherwise, it's false. And the memory aid is it's true if and only if they match. An example, construct a truth table for the statement P if and only if not Q. And by the way, when you say biconditional in that double-headed arrow, you say if and only if. So P if and only if not Q. So I'll build my truth table, and as we've done before, adding a preliminary column for that not Q that appears as a piece of the final statement. So I begin my work by taking the Q and changing it to not Q. So I change all the truth values in the Q column to their opposites to get not Q. Then I look and I notice in the final column I have a P on the left of the if and only if symbol. So I'll move those P values from the far left underneath the P. And then on the right side of the biconditional symbol I have the not Q. So I'll move the not Q values underneath. And then I notice that the symbol is the if and only if, the biconditional symbol. And then I've got to remember that the memory aid for biconditional is it's only true if they match. So you're going down and scanning and looking for matches. True if and only if false is not a match, so it's false. True if and only if true is a match, so it's true. False if and only if false is a match, so that's true. And false if and only if true is not a match, so that's false. And there's your truth table. This is again a visual aid to let you see all 5 of the truth values so you can remember these, and underneath them you have the what I call the memory aids. With the negation, you switch the truth values. True becomes false, false becomes true. For an and, it's only true if they're both true. For an or, it's only false if they're both false. For an if then, it's only false if P is true and Q is false. And for the biconditional, the if and only if, it's only true if they match. And then we've added these special cases. From section 2, we had De Morgan's laws, and from our just immediate discussion, we added 2 more from section 3.3, and those are the equivalent disjunctive forms of conditional and the negation of a conditional, which puts it in the conjunctive form. In other words, disjunctive form is the one with the or, and conjunctive form is the one with the and. So this page summarizes pretty much the basic tools for sections 1, 2, and 3. Let's do another example with the disjunctive form of conditional. What if I ask you to write the conditional in its equivalent disjunctive form? If x is an irrational number, then x is not a terminating decimal. Just proceed as before. The x is an irrational number is the P. X is not a terminating decimal is Q. So you want to take that and turn it into the right-hand side of the equation, which says not P. x is not an irrational number, then the disjunction, which is the or, and then the q, which is x is not a terminating decimal. So you put not p ORed with q, and you get the statement x is not an irrational number or x is not a terminating decimal. Simple enough. If you wanted to add the word either to make it sound a little bit better in English, you could. So if you wanted to make it sound maybe slightly less stilted, you could add the word either in front and say either x is not an irrational number or x is not a terminating decimal, but that's optional. You don't have to do that. Now let's do another example with the negation of a conditional. That changes it into conjunctive form, in other words, to something with an and. What if the statement were, if pigs had wings, pigs could fly? Again, P would be the statement pigs had wings, Q would be the statement pigs could fly, and you want to change it into the right-hand side, which is P and not Q. Well, P is the statement pigs had wings, so you just write that down. The tense doesn't much matter. It might sound better as has or have instead of had, but otherwise that's not really important. But the important part is that you've got to get the and. The conjunctive form produces an and between the statements, and the last statement is the negation of Q. Q is pigs could fly, so not Q would be pigs couldn't fly. Or again, you're not worrying too much about the tense exactly. You just want to make it sound a little better. So you might say something like pigs have wings and pigs can't fly. Not worrying too much about the tense of the verbs. You could change it even to something like this. Pigs have wings and they can't fly. The exact wording is not important. It's the structure that's important and the meaning behind what you said. We talked a little bit earlier in the previous section about the way that WebAssign presents some of these truth tables. I want to go back to a problem with the conditional and biconditional that presents the table like you'll see it in WebAssign. And here's an example. They're asking you to complete the truth table for this compound statement involving a biconditional. You start off, as you always do, with the simple stuff. You have a Q column which you want to fill in, so you take the Q values that you already know about and just move them underneath the Q. Then you move over to the not P, so you're going to look at the P column and change all the truth values to their opposites, so the true becomes false, the true becomes false, the false becomes true, and the false becomes true. Then you've got to realize you're working with an and. So the trick for and is that it's only true if they're both true. True false is not both true. False false is not both true. There's a true true, it's true, and the last one is not true true. So there's only one true in that set, and that's the true implies true. Anything else for an and is false. And remember, we talked about this before, once the Q and not P column have been used to produce the and column, those shaded columns are essentially used up. You're only paying attention to that circled column under the and. Then you move over to the other side and you're going to put the not P in. So you go to the P column and you change all the truth values to their opposites. True becomes false, true becomes false, false becomes true, false becomes true. And notice I've shaded the column under the and because, as I said earlier, the Q and the not P produced that and column in the middle, and so they've been sort of, in some sense, used up. So you don't pay attention to those two columns anymore. You're only interested in the and column on the left side of the if and only if, and the not P column on the right side of the if and only if. And remember, for an if and only if, a biconditional, it's only true if they both match. You notice the very first case, they're both false. That's a match, so it's true. Second, both false, they match, that's true. The third one, both true, they match. The fourth case, false and true, they don't match. So the only false is the very last row. The others are true. And there's the truth table for the compound statement. Let's practice a few more things. Is this true or false? 5 equals 8 if and only if 6 is equal to 4. Remember, this is an if and only if, which is the biconditional. It's only true if they match. If you go back up and look at this statement, 5 equals 8 is false, 6 equals 4 is false, and the if and only if is the double pointed arrow, or the double headed arrow, and they do match, so the statement would be true. Another example. This one has a little twist to it. True or false, assuming x and y are real numbers, 2x minus 1 is equal to 11 if and only if x is equal to 6. Now this is still a biconditional, but the best strategy when you have variables in these things is probably to go ahead and solve for x when they're not solved for x. So I would say take that 2x minus 1 is equal to 11 and say, well, add a 1 to both sides and divide by 2, and you end up with x equals 6 if and only if x equals 6. Now, obviously, they're going to match, right? Because you've got the exact same thing on both sides, so how can they not match? It's easy to see that those left and right-hand sides are going to match all the time. If x is equal to 6 on the left, it'll be equal to 6 on the right. If it's not equal to 6 on the left, it will not be equal to 6 on the right. So they will match each time. So even though there's a variable in there, I can see that the left and right-hand sides will match no matter what the value of x is. So the original statement is definitely true. Let's look at this one. Is the given biconditional true or false, assuming that x and y are real numbers? The biconditional says x squared equals 4 if and only if x is equal to 2. Now there are two cases to check depending on whether the statement x squared equals 4 is true or false. So in case 1, we can assume that x squared equals 4 is true. Now if x squared equals 4 is true, we want to know about what that implies about x being 2. Remember, a biconditional is only true if the truth values of the left statement and the right statement match each other. So if the left statement, x squared equals 4, is true, then in order for the biconditional to be true, then the right statement, x equals 2, has also got to be true. But think about that. If x squared equals 4 is true, do we know that x equals 2 is true? Think about that a minute. If x squared equals 4 is true, is x equal 2 true? Not necessarily. If x is equal to 2, then x squared is equal to 4. That is a true statement. But if x is equal to minus 2, which would mean x equal 2 is false, x squared is still equal to 4. That would still be a true statement. So we don't necessarily know that x is equal to 2 just because x squared is equal to 4. That means we can't guarantee that the two statements match truth values, which is the only way that a biconditional is true. Because if x squared is equal to 4, all we know is that x could be 2 or minus 2, not just 2. I will say that there might be an easier way to think this through. When you have a problem with a variable in its a so-called open statement, it might be easier just to think it through without breaking into cases. And what I mean by that is, if x squared is equal to 4, we know from algebra that x is either 2 or minus 2, but the right-hand statement just says x is equal to 2. So we know that x could be 2 or minus 2, not just 2, which means we can't guarantee that the truth value of the left statement matches the truth value of the right statement. Therefore, the biconditional is false. So you might find it a little bit easier just to think about it that way. It's up to you. This is sort of a monster-looking thing, but it's no harder. It's just more work. So let's go straight for it. The first thing I would do is take that open P column and move the P values on the far left column over. Then I'd move over to the Q's and do the exact same thing, move those Q values over. Then I would attack the implication. Remember the implication, it's only false in the true implies false case. So I'm looking for true implies falses to turn to false. Otherwise it's true. So I just scan down through there and notice there are only 2 cases that give me true implies false. So I'm going to call those false. There aren't any more of those, so the rest of them are true. So also, I said earlier, and I think I'll actually illustrate it here, that once the P and the Q are used up to produce the implication, they're essentially gone. So I'll actually shade them out just to emphasize that once the P and the Q is used to produce that value under the implication symbol, they're used up. They're not important in the table anymore. Next, I'll notice that I have an R column over there that needs filling in. So I'll take those R values and put them in. And I notice I have a not P column, so I have a P column. So to do a not P column, I just change them all to the opposites. All the trues become falses and all the falses become trues. And then I notice that I have an and between them. An and is only true if they're both true, and I scan through there and only see two cases where they're both true, so those will be the trues. Everything else will be false. And again, I've used up the R and the not P. By producing the and, I used up those other two columns. I'll actually shade them out just so your eyes don't focus on them anymore. And as I move across, I see that there's another R column, so I'll move those R's over. And I see there's a not Q column, so I'll take the Q column from the far left and change all the values to the opposites. All the trues become false and all the falses become true. And then I notice I have an OR. An OR is only false if they're both false. So if I scan down through there, I see two cases where they're both false. So that makes a false. Everything else will be true. And again, the R and the not Q column have been used up, so I'll sort of shade them out so your eyes don't focus on them anymore. Now I'm going back across here, and I notice I have to fill out this OR column. I couldn't fill it out until I got trues and falses on both sides of it, but I do have trues and falses on both sides, and I remember that an OR is only false if they're both false. So if I scan down through there, I only see two cases where they're both false. So I'll change those to false. Everything else will be true. Now those two columns got used up. Look at this one more time. I produced this OR column by using the two columns on the left and right, so they get used up. I shaded those columns out so that your eyes don't focus on it. So now all I have left is that implication, and on the left side of the implication, I'm looking at that one column that's not shaded out, and on the right side of the implication, I'm looking at the one column that's not shaded out, and I noticed that with an implication, there's only one false case, and that's true implies false. So I scan through there and find the two cases that have true implies false and make them false, and the rest of them will be true. And there you go, you have your truth table.